Hello students, in this video we'll discuss a problem relating the null space of a matrix to the null space of a matrix that has been multiplied by an invertible matrix, and likewise the image of a matrix when multiplied by the invertible matrix. So let's consider an M by N matrix A, and let's be given two invertible matrices and given two invertible matrices U, and this U, of course, is going to be an M by M matrix, an M by M matrix, and V, which is going to be an N by N matrix over here, right? So what I can do is I can form two other matrices over here. So let's form a matrix B, and B is going to be this matrix U, which is M by M times A. So that makes sense. So what will this matrix B be? This is also going to be a what? This is going to be an M by N matrix over here. Great. And I can form C, which is going to be A times V, right? Now V is N by N and A is M by N, so this is going to be an M by N matrix as well. Okay? And so now we're getting a couple of results about null space as an image, right? So in other words, I can prove that the null space, here's a proposition, the null space of the matrix A is the same as the null space of the matrix B, null space of B, which we know, of course, is just the null space of U times A. And then the image of A is the same as the image of C, which is the image of A, V. Okay? So let's call this over here 1, and let's call this over here 2. We're going to prove 1 and 2 by inclusion arguments over here. So let's do it. So here's the proof. Proof of 1. Circle these over here. So proof of 1. All right, so this is an inclusion, right? So let's let X be in the null space of A. Then AX is equal to 0 by assumption. And I'm going to suppress the vector notation on 0, right? So this is going to be the 0 vector, but if I forget the vector notation on 0, it's always assumed that this is a vector. It has to make sense, right? So in other words, I have to input a what? I have to input an n-dimensional vector. So this x is an element of Rn over here, and this is the m-dimensional 0 vector over here, right? So it's always important to remember where these things are moving from. So this is the n-dimensional vector x, and that's the m-dimensional 0 vector over here. So this is an n, this is over here is an Rn, and this over here is an Rm. Okay, so it's important to remember what that is. Now, of course, since A is invertible, we know the only thing, so of course, now we know that U is invertible. So now, let's look at UA of X. Well, UA of X is going to be U of what? Of the m-dimensional 0 vector. And of course, U is a what? U is going to be, is just as a matrix, of course, any m by m matrix maps 0 to 0. So this is going to be the m-dimensional 0. And that implies that X is where? This implies that X, thus, X is in the null space of UA. Okay, so that proves one inclusion over here. So I just proved the inclusion that null of A is contained in null of UA. Great. Let's do the other direction. Let's let Y be in null of UA. Okay? Then U of AY is the m-dimensional 0 vector. And this implies that AY is in the kernel of U, right? So AY is in the null space of U. But since U is invertible, the null space of U is just the 0 vector, the m-dimensional 0 vector, right? And that implies that AY is equal to the 0 vector. And that implies that Y is in the kernel, or the null space, is the null space of A. And therefore, I've just shown what? I've therefore just shown that the null space of UA is contained in the null space of U, so I've just reversed the inclusions over here. So these inclusions over here, so this contained in this gives me the opposite inclusion, and we've just proven number 1. Excellent. Okay, that's great. Let's prove number 2 now by the same sort of reasoning. So the proof of 2 is very similar. So let's do the, what's the easy direction now? The easy direction is to start over here, right? So let's let y be in the image of A times V, right? That means there exists a W in Rn, right? Because now it's n by n, hence there is a x in Rn such that y is equal to a v of x. By definition of what the image is, right? I can plug an x into a v and get my y out. But now, of course, that says that vx, if I input vx to a, I get y. So that says that what? That says that y is in the range of a. So this implies that y is in the range of a. Or the image of A. So I've been using image of A, so let's change that to image, right? I'm using kernel and range and image because they all mean the same thing, they're just different notations, right? So let's say that y is in the image of A. That's great. That's one inclusion. Now conversely, let y, let's say z actually for context, be in the image of A. Then there is a W in Rn such that A of W is equal to this vector over here, Z. By definition, the image of A, right? But since V is invertible, there is, let's say, U, vector U, in Rn, such that V of U is equal to W. Okay? And that says that Z is equal to A of W, but A of W is equal to V of U. So that says that Z is in the image of A of V, and therefore the image of A is contained in the image of A of V, and the image of AV is contained in the image of A. So that proves part 2. So that's the proof of part 2, right? Now the cool thing about this is that what I can say now is I can say interesting things about what the image of this thing happens to be, right? Because now I know that the null space of this thing is the null space of this thing, so I can use the rank nullity theorem to prove other results about about the null space of UA and null space of AV and the image of UA and the image of AV, and using the rank nullity theorem, right? And we'll see how we can use that in further videos. Thank you very much.